Hello, everyone. My name is Professor Keith Hawkins. I'm an assistant professor of astronomy at the University of Texas at Austin. And I arrived in Texas about 2 years ago and very quickly learned about one of the jewels of Texas, which is McDonald Observatory out in West Texas. And it is pictured here in the background image. And I am an astronomer and focus on a field called Galactic Archaeology. That kind of is, I like that term because at cocktail parties, I can introduce myself as the Indiana Jones of the galaxy. But before I get into what galactic archaeology is and what we do in terms of finding fossils in the sky, I wanted to give you a little bit of information about me as a scientist, what I do, how I got interested in astronomy, what my path was in becoming an astronomer. So I actually got into astronomy at a very, very young age. And unlike most people who look at the sky and just get enamored with it, I actually really hated science and very much hated astronomy and physics when I was very young. But I got into astronomy because of a crush on a girl. My very first crush, in fact. And she would check out these encyclopedias of astronomy just to look at the pictures. This was about fifth grade. And we would check out these encyclopedias, we'd look at the pictures and chat with each other, and we would often get in trouble with our teacher for talking way too much about black holes and if there were other planets out there and if there were other black holes out there. And she moved away, and I was very sad about that. But by the time I got to high school, astronomy became its own full-blown passion. And when I was in high school, in fact, I went to the International Science and Engineering Fair for a project that I did on astronomy, and I won one of the top prizes, and then I gave her my medal years later after seeing her again. And so after I went to high school, I went to college at Ohio University, where I majored in astronomy, astrophysics, and mathematics. I also have a degree in African studies. So I took a semester off and actually taught middle school math and science in the West African nation of Ghana. And there I learned I will never, ever, ever become a middle school teacher because I really enjoy teaching at the college level. And when I was at Ohio University, I had this wonderful opportunity to not only major in astrophysics, but also visit these wonderful different telescopes from around the world, like Palomar observatories in California, or the Kitt observatories in Arizona, or the Keck telescopes in Hawaii on Mauna Kea. And that really solidified my vision, my dream of becoming an astronomer. After undergraduate, I was very lucky. I actually won a Marshall Scholarship to attend the University of Cambridge in England to do my PhD in astrophysics. And that was a really cool experience. That was very much like being at Hogwarts. Hogwarts is modeled after Oxford and Cambridge. For example, whenever you go to dinner, just like in the film, Harry Potter, all of the students have to wear gowns and robes, and there is a high table where Dumbledore sat and all the professors. Yes, that actually does exist.
Let the feast begin.
So I was very lucky and spent 3 years over there doing my PhD. I became a postdoc after that at the Columbia University in New York City. And then finally, I landed a faculty job here at the University of Texas at Austin in 2018. And so what I work on here is something called galactic archaeology. And really, that's a fancy term for answering some pretty basic questions, which you might think are basic questions, but questions that we still don't really have the answer to. How do galaxies like this form? How do they evolve? How do they assemble themselves? What are the physical processes involved in forming them and assembling them and creating them and evolving galaxies and stars? And so answering these questions, that is what galactic archaeology is all about, and is basically like being the Indiana Jones of the galaxy. Except for me, unlike Indiana Jones, I don't go and search for human artifacts and fossils. I search for stellar fossils. So what a lot of people don't realize is whenever you look up at a star, every star in the night sky is a fossil. And that's for two reasons. The first is that stars themselves contain DNA, contain chemical fingerprints that generally don't change over the course of their life. And so if you look at a star that's 10 billion years old, and you look at its chemical fingerprint, kind of like its DNA, you'll be looking at seeing at what this universe was doing chemically about 10 billion years ago. So this is the same type of concept used for tree rings or ice cores here on Earth. And in addition to that, remember that the distances in space are incredibly vast. And so if you look up at stars, odds are good that the star is far enough away that you're not seeing the star as it is now, you're seeing it as it was thousands or even millions of years ago. So if you look up at the sun, which you should never do without protective lenses, you're not seeing the sun as it is now, you're seeing the sun as it was about 8 minutes ago, because it takes 8 minutes for the light to get from the surface of the sun to our eyes. And that's true for any other star in the night sky. So these are the two primary reasons why stars are fossils. And stars obviously stars are what trace out our galaxy. And this is an artist's impression of what we think our galaxy looks like. It's an incredibly beautiful barred spiral galaxy. Spiraled because you can see these beautiful spiral arms, and barred because you can see this wonderful bar in the center part of the galaxy. Now, one question I often ask my students, and anyone interested in astronomy, is, do you think that we live in the center? And the answer to that question is no. The sun and the Earth, we all live about 2/3 of the way out, about 28,000 light years away from the center of the galaxy. So this is an artist's impression of our galaxy. And if we change that to the state-of-the-art image, the best image that we've ever gotten of our galaxy, it looks something like this. So for me, the Milky Way is my laboratory. As a scientist, we often think of scientists wearing white coats and being in the lab. That's not what being an astronomer is like. Being an astronomer is looking at data, going to telescopes, sitting in front of a computer and computer coding. That's what really being like an astronomer is like on an everyday basis. And so for me, the galaxy, the Milky Way, is my laboratory. And this galaxy is structured with lots of different things in it. For example, it has a bulge at the center part of the galaxy, and that bulge is very metal rich. Lots and lots of the different heavy elements, the irons and nickels and cobalts and chromiums of the periodic table exist there. Then the galaxy has a really beautiful thin disk. It's kind of like, it has the same aspect ratio of a French crepe, roughly. And the thin disk is metal rich, and the sun, our sun and our Earth live inside of the thin disk of the galaxy. The galaxy also has a thick disk, which is, not super metal rich. It's a lot less metal comparatively. And then on the outskirts, we have the stellar halo. And there's a lot of debates about these components. We don't really, we think that these all exist, but one of the wonderful things about science is, of course, that there is a lot of unknowns out there, and we're still trying to get to the bottom of it. And so my group at the University of Texas at Austin is the Galactic Archaeology Lab, and this is us pictured in the shark tank. It's actually known as the shark tank because there's a inflatable shark. I'm not sure why there is, but this is my research group of various undergraduate and graduate students. I have 4 graduate students, a postdoc, and about 5 undergraduates in my group. And some of the questions that we try to wrestle with on a daily basis are things like, how did the Milky Way come to be? How did its different, I've told you that it had 5 different components to it. How do those components form? What are the physics? What's the physics that's important there? What are the timescales involved? How long does this whole thing take? How do stars work, for example, inside of our galaxy, and many, many other questions. So these are the types of questions that as an astronomer, I look at and try to answer. And any scientist has tools. For an archaeologist, they might have tools that look like this, but as a galactic archaeologist, my tools look very different. My tools generally come in 2 forms. I can use simulations like this. So this is a simulation about how galaxies form. And what you're going to see in a simulation is little proto-galaxies, small little sub-galaxies that aren't yet forming. They're about to form their stars. And what's happening is the force of gravity is bringing those galaxies, those proto-galaxies together. And the galaxies are harassing each other, forming these beautiful arcs and tails and streams. And in general, actually, these galaxies will merge, as this galaxy about here is going to eat up all the other galaxies around it, in a process that we call galactic cannibalism, where the largest galaxies eat up the smaller ones and grow and grow and grow into larger forms. And so simulations are a way we can understand this, and what we do with simulations is we put all the physics that we know into a computer, we let the computers run, and we we observe a simulated version of the galaxy through our simulations. And we can make models of the positions and motions and chemistry of the stars in our simulations. But then the next important process of science is not just using that simulation to make a hypothesis, but then going and testing that hypothesis or with an observation, comparing with observations. So the second tool that I use as a galactic archaeologist is spectroscopy, which is a process that we use in order to measure the chemical fingerprint, the chemical DNA of stars. Spectroscopy operates in a very similar way as the Pink Floyd album cover Dark Side of the Moon. You basically take white light, you pass it through a prism or a grating, it breaks up into the beautiful rainbow, as is shown here from that album cover. What they don't show you, however, in the album cover is that if you look hard enough at that rainbow, you actually see dark bands that appear. And so this is actually the sun. If you take sunlight and you pass it through a prism, you actually will get something that looks like this. And each one of these dark bands that are appearing in this spectrum, as we call it, is caused by the absorption of a different element in the atmosphere. To someone who's trained, an astronomer who's trained, I can tell you, for example, this is because there's hydrogen in the atmosphere of the sun. This is because there's a bunch of sodium in the atmosphere of the sun. These three lines here that are really deep is because of magnesium in the atmosphere of the sun. And so each element has a fingerprint within this beautiful array of the color spectrum, and we can actually use it to map out the different chemistry of the different chemical patterns in the stars. And UT Austin is one of the best places in the world to do this because we have access to many telescopes out in West Texas at McDonald observatories. In addition to these chemistry, we also use the position and motion of stars. And I've been using a spacecraft called Gaia, that's pictured here. Gaia is a European Space Agency mission. Its tagline is called the Billion Star Surveyor, and it's going to produce the most precise 3D map of the galaxy ever attempted by human beings. To do this, it will map out about 1 billion stars in the night sky. That sounds like a lot, 1 billion. It's about 1% of the galaxy. It's a very tiny fraction of the galaxy, but it's the largest that we'll ever be able to do. It costs about €1 billion, so it's about a euro per star or so. To give you an idea of why Gaia is going to completely revolutionize things, just here we have, if we go back to our beautiful image of the galaxy, the sun is sitting here about 2/3 of the way out. Everything we used to know previous to the launch of Gaia about our galaxy was really kind of focused on this small little region here that we got with the previous space mission called Hipparcos. Gaia is going to expand our view of the galaxy from this small little circle to this much larger circle. Really, really, really large expansion in what we're going to be able to see in our galaxy. And so that's one of the reasons why I'm really excited right now to be an astronomer and why it's so exciting to be a galactic archaeologist right now. And so with Gaia plus all of these large surveys, we're really planning to do this hopefully this wonderful map of the galaxy. And the thing that my group is particularly working on is something that I like to call chemical cartography, which is this idea of basically making a chemical map of the galaxy. Kind of like the first explorers, exploring, the New World would go out and make the first set of maps. Well, we're doing that now, but we're doing it with the galaxy for the first time. And we're not just drawing out where the stars are placed. We're also now color coding those stars by their chemical fingerprint. And so this is a little video showing stars. Back in the background, you see a kind of a rendering of what we think the galaxy looks like. And in the foreground is real data from real telescopes, where each point of light is a star, where we color coded that star's chemical abundance by how much magnesium is in the atmosphere of the star. If you see the star looks blue, it has not that much magnesium. If it's green, then it has lots. And you can beautifully start to now unfold the galaxy in this truly multi-dimensional way that we've just never been able to do. And so I'm working with my 2 graduate students who are pictured there, as well as an undergraduate student, Maya Sinha. And we're all working together on building this map. This map currently exists now in the Hayden Planetarium in New York, but unfortunately, the city of Austin does not have a planetarium. So we're currently working with a virtual reality gaming company in downtown Austin to make a VR version of this. And we hope to bring it to museums and classrooms, hopefully in the near future. I kind of want to end with where I think galactic archaeology is going as a science, as a field. One of the wonderful things about galactic archaeology is that we're answering questions about how galaxies in general form, but using our own galaxy as a laboratory. And the reason why we do that is because our galaxy is pretty easy to measure. It's pretty easy to understand. or not understand, but it's pretty easy to observe because everything's relatively close. What I think galactic archaeology is going is not just doing galactic archaeology using our Milky Way as a laboratory, but using nearby galaxies as laboratories as well. So this is a beautiful image of the Andromeda galaxy nearby. We don't currently do galactic archaeology in Andromeda just because it's too far away to measure individual stars. But we're now starting to get to a stage in astronomy where we're able to do that. And we can start to now piece together the structure and history of another galaxy, the Andromeda galaxy. And we're not quite there, but in 5 or 10 years from now, I think that we will be there, where we'll start to be able to measure the chemical fingerprint of individual stars in Andromeda and do what we're doing now in these chemical maps, but do them in Andromeda for the first time and really start to piece together and answer that really important question: how do galaxies form? So Gaia is a spacecraft that measures these things called parallaxes, which is the angle of change between looking at a star on one part of its orbit versus another. It's very similar to the method that we use with our eyes for depth perception. So our eyes are separated, and if you ever notice, if you hold up your thumb and you put your thumb really close to your face and you blink your eyes back and forth, you'll notice that your thumb, the relative position of your thumb, changes very, very much compared to the background. But if you put your thumb really far away, you notice that the angle is much smaller. So that's called parallax. That's exactly what Gaia is actually doing in the sky. And so the Gaia will get better for as long as it stays up. So if the longer it stays up, it will get better. So I think we're going to expand the circle out to here actually, and get Gaia actually can get these galaxies. These are the large and small Magellanic Clouds. I think Gaia is actually going to be able to do individual stars and really precise distances to those, which are very far away, if we let it stay up for 10 years, for example. Especially in astronomy, the skill set of what an astronomer looked like even 15 years ago is very different than what it looks like today. So in today's market, being an astronomer and really being a scientist, I think the one primary skill that you have to be able to have is being able to understand how to apply the scientific method in very complex problems. And so that's learned at a very young age. We all learn about the scientific method, in middle school or even in high school again, sometimes in elementary school. But being able to apply that is incredibly, incredibly important. And then beyond that, in addition to that, you want to be able to have strong skills in, for my type of science at least, mathematics if you can. A lot of math goes into being an astronomer. A lot of physics goes into being an astronomer. And so you need to have relatively good math skills and physics skills. Although the reason why I say relatively is because we're all taught, or not all, but many of us, especially those of us who are Black and brown and women, are often taught that we're bad at math. When in fact, it's not that we're bad at math, we're just conditioned to think that we're bad at math. And so it's this fine line that you have to walk with students, that I have to walk with students when I'm teaching, about telling them that math is important, they need to be good at it, but also recognizing that we're told that we're bad at math. So by saying that, I could be self-selecting out students. So math and physics skills are important. But I think probably by far one of the most important skills in astronomy nowadays is computing. You have to know how to compute a program nowadays. Everything we do is computing based. And so being able to learn how to code in Python, or knowing C or C++ or Java are very, very useful skills to have. And it's something that we don't often have in our curriculums for astrophysics majors, to do a CS class, as a computer science class. But I think that's another skill that really is, I spend most of my time computer coding, actually. Coding up how to work with and deal with the large amounts of data that I'm receiving from the space telescopes and the ground observatories. So I think those are the types of skills that you're going to want to have: computing skills, being able to apply the scientific method, and math and physics skills. Yeah, so diversity is really important. It's an important part of doing good science. And a lot of that is because the reality is science is a creative process. And a lot of people don't realize this, but science is a very creative process. And having a diverse group of people participate in science means that a diverse set of opinions are going to be coming to the table, diverse way of looking at things are going to be coming to the table. And study after study has shown that diversity in the workplace, especially in the science workplace, really improves efficiency, but it also improves the type and quality of science that gets done. And in addition to that, it also is an important part of retaining and building a sense of community for people. And so I am an African-American astronomer. I'm one of the very few African-American astronomers that's out there. I'm mostly went to universities and colleges that are predominantly white. And so it is extremely discouraging as a student of color to be in an environment where you have no one that looks like you, no one that experiences the things that you experience, no one that experiences the racism that you experience. And it's an incredibly isolating experience. And in order to minimize that, you really need to build a diverse workforce. And so, that means needing to have diversity, not just in students, but at all levels, whether it's faculty at universities, whether it's research scientists, whether it's staff, whether it's students. There needs to be diversity at all those levels so that there are support networks for people who are diverse or underrepresented, but also struggling and going through kind of a rough time with all of the various things that are going on. One of the real challenges, I think, is that, especially for underrepresented minorities in the field, it can be really challenging because they're working and focusing on their science, but then they have this extra burden on top of them where they have to also figure out how to navigate this very white space. And that creates an environment where those scientists often don't have the ability to contribute nearly as much because they're dealing with all these other things on top of it. And so that's something that, with a greater diverse workforce, that will be minimized, and people of color will have more of an opportunity to participate equally in the field that I don't think we currently have. So I think probably the most important piece of advice I can give is to persevere, but also never lose the enjoyment. Because what makes, I think, all of the scientists that I try to model myself after, what makes them incredible scientists is that they're still truly passionate about their science. And if you're passionate about your science, that will leach off into other people. Other people will get interested and excited about your science. And that's hard to maintain, I think, over the course of a career. And so, the piece of advice I would give to a middle school student is try not to lose enjoyment of it. Just go out there, explore, and enjoy, what science has to offer. Don't limit yourself.